Good afternoon, everyone. I hope you're enjoying the conference. I sure do. Yesterday, I was at the speaker's dinner, and when we arrived back at the hotel, I looked up at the sky, and unfortunately, I couldn't see a single star because it was cloudy. But even if it was not cloudy at all, you still would not be able to see that many stars because in urban areas like Paris, light pollution prevents you from seeing many stars. If you would go to a more remote area like this, you might even see the Milky Way. Personally, I haven't seen the Milky Way like this myself, so one day I hope to see it. But people have been looking at stars for ages, and we've been trying to understand them, map them, document them, attributing religious gods and events to the stars. There are even suggestions that we are made out of stardust, so stars are kind of special to us. And if you want to take a closer look at stars, you might want to take your telescope and have a closer look at a star. But if you want to make accurate measurements of a star, then looking through a telescope from Earth is a little bit difficult because the Earth's atmosphere will distort your measurements. So therefore, in 1989, people were quite excited that the European Space Agency launched the first optical space telescope. It was a little less than a year before the Hubble Space Telescope was launched. And this telescope is called Hipparchus, named after one of the first astronomers. And the mission of Hipparchus was to take accurate measurements of about 100,000 stars. And the measurements were more accurate than had ever been done before. The European Space Agency also has educational programs and outreach programs to tell the general public more about science, astronomy, and the missions that they do. And for that, they asked me to create a visualization of the Hipparchus star catalog. And let me show you this project. And it's a live demo, and I'm going to look at that screen. So if I'm not clicking at the right button at the right time, then bear with me. So this is the starting screen. You see the sky. And when you click the start button, this is the main screen. On the right, you see a short description of the current view. Here on top, you see a few suggestions how to interact with the visualizations. Here on the left, you have a set of toggles that help you orient yourself a little bit better. Here at the bottom, there are several buttons to navigate to the various views of this visualization. And here's the main control for this specific view. And this specific view is about the apparent magnitude. And the apparent magnitude is about the brightness that you measure from a certain point. And in this case, it was the satellite itself. And so you can change the brightness so that you can see more stars or less stars. The way you can interact with it is you can really move around, and you can zoom in and zoom out. And what I personally really like is that if you look at the constellations, you see that once you zoom out, then you realize that the choice of stars of the constellations are really a human choice from Earth, and not stars that are close together or something like that. The next view is about the absolute magnitude, and you already saw it a little bit. Most of the stars become bigger. Some of them become smaller, and the absolute magnitude is the brightness of a star as if it would be on the same distance from Earth or the observer. And basically, that's what I'm doing here. So it's not realistic, of course, but I'm putting the stars at the same distance from the observer. So this is what the concept of the absolute magnitude. The next view is the Hertzsprung-Russell diagram, and this is a well-known diagram in astronomy, and it tells you something about the life cycle of stars. Horizontally, there's the temperature. The cooler stars are on the right, the hotter on the left, and this is the brightness, the brightest stars on top, and the faintest stars at the bottom. I have learned doing projects for the Space Agency that you always have to look real close at your axis because they often flip axes and do things the other way around. But this is the correct way to show the diagram. Here you can switch between colors, which is a kind of an indication of the star temperature. This is I think, my favorite view of this visualization. This is a stereographic projection of all the stars. And so you can still move around, but as you can see, it's a kind of different way of zooming from the three-dimensional view. And if you look at the stars, you might think that they are stationary in the sky, but they actually are all moving. And so with these buttons, you can start a simulation of how the stars are moving over time. You can move forward in time, and you can move backwards in time. And finally, the final view allows you to play around with all the controls that you have seen in the previous steps. So you can turn on all the stars, you can give them colors, move them around, switch between 3D and stereographic and things like that. And I don't know if I can find one right now, but there are some stars, yeah, maybe over here. There are some stars that move in clusters, and that's quite interesting, of course. So let me see if I can back to my slides. So the reason why I'm telling you this is because today I want to share with you some of the ideas and thinking that I had when creating many data points in the browser, because this just runs in the browser. So it's maybe some simple tips, maybe some strategies of how I approach my project. And one of the things that I often realize when doing a little bit more complex projects like this is that I stack layers of web technologies. So HTML is very good for user controls. SVG, as you can see, is a little bit more happy than HTML because he can take on more shapes. Well, for both HTML and SVG, you have the DOM at your disposal, so it's easy to manipulate it and to detect events like mouse over. But once you have many data points, SVG may not be the best choice, because if you have to manipulate a lot of elements and it becomes really complex, then you will start noticing that your performance may go down. So an alternative could be using the canvas element, and you have two flavors, two-dimensional and three-dimensional. And in both cases, you're basically drawing pixels. And when you're animating, you just redraw an image several times per second. Now, the 3D canvas is particularly interesting because you can make use of hardware acceleration. So your graphical card will do a lot of the processing, and it will do so in parallel. So that means that you can have lots of data points in the browser with good performance. So let me give you a quick introduction of how you would create a 3D scene. So what you first need is a scene, and then you have to add a camera in order to look at things. Then you have to add some vertices, some points in space, which is your geometry. But in order to see your geometry, you also need to add a material. And this combination of geometry and material is a mesh. And of course, you can add several meshes to your scene. Now, for your material, there's one special type of material, which is a shader material. And the shader material has two components, a fragment shader and a vertex shader. And from JavaScript, you can send variables or values to your shader. Basically to your vertex shader, and your vertex shader can pass on variables to the fragment shader, if you like. The vertex shader is used to manipulate your geometry, and the fragment shader is used to actually draw the pixels. But as you can see, the arrows that I've drawn there are going into the vertex shader and then into the fragment shader, and there's nothing coming out of it. So that's a little bit of a challenge there, because, well, first of all, shaders can be quite complex, actually. If you look at the code, well, it became a little bit hard to understand, and shaders have their own data types. They have their own, there are some limitations to the number of variables that you can pass to shaders. It's much harder to debug shaders, so it's not really easy to create shaders. But at the same time, when using a canvas element, for instance, drawing text in canvas creates, well, the quality of the text is not usually that good. So if you look at this image, what I wanted to do was to have HTML shaders. So I really had those two layers, like the 3D canvas, and on top I had HTML. And I wanted to use HTML labels because of higher quality labels, and also because I wanted to have them a constant size and regardless of the 3D position. But since I don't get any information back, so basically, which is the calculated position of these stars, I don't get this information back. I have to do the calculation of the motion again in JavaScript just to move the labels. So what you see in this short video is I turned off the canvas, and this is just, again, the algorithm calculating the position of the stars, but then just applying it to the labels. So that's one of the interesting things that I, well, kind of discovered, that you have to do, things can become quite complex to do even simple things maybe. Another project, which coincidentally uses 60,000 points as well, just like this Star Mapper project, is a project about water. And the Dutch special envoy of the Netherlands, which is a government official, and he travels the world and promotes water issues and water management, and probably mostly water management the Dutch are doing. But he, earlier this year there was World Water Day, and for this event he had an ambitious idea. We need to create a platform where users can contribute stories on living with water. And they have asked the Deltares, which is the Dutch Research Institute on Water, to create this platform. And I was asked to create a visualization for this platform. And it looks like this. The visualization itself, as well as the interaction, is a little bit simpler than the previous project, but you can move the globe around. You can, again, zoom in. And every circle on the globe is, well, basically the link to a story. And once you click on it, you see that the globe will center on it, and then you can read a story. The stories are organized according to kind of a book metaphor, so you have books with chapters and pages and things like that. So once you start scrolling and your book has more chapters, but with a different location, you can see that the globe is centering on that new location. There are three main themes for this project. There's too much water, too little water, and too dirty water. And if you click on one of these other icons, you can see that the color of the globe is, and the particles of the globe is changing. And yeah, going back is not the easiest thing. And this is for too dirty water. So for this project, just since this is not a really complex project, what might be interesting to know is that if your geometry itself doesn't change really that much, it's actually quite easy to get high performance. When all your particles are moving and you have to do a lot of calculations, then it's much more difficult. But this data I use to, well, let me first zoom in a little bit more so that you can see it a little bit closer. Because there are squares that are kind of nicely aligned. Yes. The data comes from this website, and this website is the World Resources Institute, and they've created this product, and they have several indicators on risks on water. And you can download their data as shapefiles. And so you get a set of polygons, and we picked 3 indicators that were the closest match to the main themes: too much, too little, and too dirty water. The next step, in order to create these particles on the globe, was to generate a set of points. And, well, generating points on a sphere, there are several ways you can do that. You can, of course, do that randomly, but then you don't get this nice layout. So there's this algorithm that I use, and as you can see, the image you can get nicely equally distributed set of points. If you convert these spherical coordinates to Cartesian coordinates again, then you get something like this. And if you then open this up in, well, for instance, a tool like QGIS, and then what you basically can do is for each point each of these points, you can sample what the data values are for your polygons. And that's a nice way to transfer, well, data from polygons to points. And that's how I got the data set. Another thing that we put some effort in is optimizing the data set itself. And, well, it may be kind of obvious things to do, but creating a small data set is really makes sense, especially if you have lots of data points, because small changes can have, well, relatively big effects. So basically, a data set consists of characters. So what you want to do is get rid of as many characters as possible. So if you have new lines or white spaces or things like that, you can remove that. And another one you might not maybe directly think of is the precision that you generate from, I don't know, another piece of code may be much too high for the visualization that you need. So you can get rid of quite a few decimals. And that will save you, well, for 60,000 points, it can save you 400 kilobytes. Another one, so imagine that you have latitude and longitude, and you have a data point for every latitude and longitude angle. You can see that the numbers are repeating. One thing I did was you can also group by one of those repeating values. It's maybe also not what you think of because it's a numerical value, but if it's a fixed value, it can really save up some space. And the final thing, if you have a nested array, you can also flatten that array so that you, in your code, you have to go through the array in steps of 3 instead of steps of 1. But you can get rid of quite a few brackets. The final project that I would like to show you is a project I would like to show in this tab. And it's a project, and it was released, I think, 3 hours ago. So it's brand new. And this is a project and also for the European Space Agency. And maybe you've seen the news about 2 weeks ago, and it was the European Space Agency had another mission, a kind of a follow-up of the project I showed earlier. And this is called Gaia. And Gaia was also a telescope that would take measurements of stars, but this time not 100,000 stars, but 1.3 billion stars. And it was 200 times more accurate than has been done before. So that's really, really impressive. And for the same kind of outreach to the general public, they wanted to, well, to create a visualization, and they asked me again to do it. For this visualization, I applied a scrolly-telling approach. So basically, the kind of communication pattern that I tried to apply here was when I was talking to the people from the space agency, what I noted was that they were really excited about the size and the increase in accuracy of the data set. So I was thinking about ways to, well, kind of communicate the size of the data set. But 1.3 billion stars in the browser is maybe a little bit too much. So the way I try to communicate it is kind of set the frame for a user, and then when he continues, he realizes, well, this is actually not the right frame. I should look at it like this. So here, the first way that I apply it is by showing an image where you don't really know yet what you're looking at. So then, if you continue scrolling, then it will explain that you're actually looking at an image of stars, and it is, in fact, 39 million stars. And that's really a lot of stars, as even compared to the previous project. But if you continue, so you start to realize that's a lot, but then the image starts to scale down in size, and you don't know yet where it's going to stop, and you don't know even why it's becoming smaller. But then at some point, the full sky map will appear, and so you see that it's just a small patch of the full sky. So then you realize that they really measured a lot of stars. This image in the background is generated by the space agency. This next image as well, they also measured colors of the stars. And at this point, I introduced the interactive part of the visualization, and these are 20,000 stars. And, well, you can see that these are clearly, well, not equally distributed over the sky, but the reason why we picked those clusters is we wanted the stars to be constantly visible in this visualization, and that would mean that we needed to have data for a number of dimensions that were accurately enough and available, and so it turned out that clusters were the best candidate to show this. So here the clusters are positioned at the position in the sky, and then here I start sorting them again by temperature, and then they are sorted by brightness, and so then you again end up with the Hertzsprung-Russell diagram. Compared to the previous one, that was more scattered. This one, because of the clusters, you see those lines there. Then the explanation continues by showing what the three important areas of this diagram are. The main sequence is where the most of the stars are. And on the top right are the red giants. So when stars become older, they become much brighter and cooler. And there are also a lot of stars, when they die, the core of the star remains and they become a white dwarf, and that's in the lower left. Now this diagram is also about the life cycle of stars, and that's one of the key things that the researchers try to get out of this new data that they've collected. And so a life cycle suggests changes over time and how things how a star changes over time. And in this case, how the star changes position in this diagram. So if you continue scrolling, again, a simulation is started and you see how stars change over time. You can also make selections, so you can look at individual clusters and how they move. And you see that the white dwarfs increase as well. And that's basically the visualization. Where's my... So you saw that the stars moved at a kind of peculiar shape, and that is because it's based on these isochrones. And an isochrone is a set of points in a diagram that are connected by a line because they have the same value or same characteristic. Horizontally, again, temperature, vertically, brightness again. But this diagram of, and each line represents the age of a star. So you could, if you have a certain point in the diagram, you can determine what the age of a star is, more or less. But it turns out that this is just one diagram for one type of stars. Mass of a star, the amount of iron in a star also determines how these isochrones will look. So what I've done in order to calculate the paths for these 20,000 stars is to collect multiple data sets of these isochrone data sets and then use multidimensional interpolation. And that would eventually result in the individual evolutionary tracks of the stars. This is a kind of debug view for me. This is actually an image of the individual tracks of the stars. This was a moment where the shape of the white dwarf was not correct. But this is also a good reminder that you should always be aware of what your data means, because otherwise you make wrong decisions. So what you see right here, you see a lot of vertical lines. And in the animation, you didn't see stars moving along these vertical lines. And the reason is, it turns out that the moment a star leaves the main sequence and becomes a white dwarf, it only takes 1,000 years. And in the life cycle of a star, that's really the blink of an eye. So in the simulation, that's instantly. But yeah, in these tracks, these lines are definitely there. Finally, I have this image. And that's the image I start this visualization with. And I personally find it quite interesting because lately I also start using, for these types of visualization, the browser as a kind of tool. Because these 39 million stars were rendered in the browser. My initial idea was, wait a second. My initial idea for the zooming was a little bit different. So I was thinking about different ideas of how should I show this many data. So if you look at the current start of the visualization, you see that the image becomes smaller, and then eventually the full sky map will fade in, and then at the end, this patch of the sky matches the full sky. But what I originally had in mind was this. I wanted to actually zoom the full sky. And these are it goes a little bit shocky, but this is really a sequence of frames that zoom the full sky, and all these frames are rendered in the browser. And my idea was that I should create a video, and then based on the scroll position, you determine the current frame. So that could be a strategy to give the suggestion that you're interacting with the data, but you're actually interacting with the video. But I wasn't able to create a video that was of enough high resolution, high quality, and enough frames in order to have smooth scrolling and a small file size. So this is just 50 frames and it's already 27 megabytes. So it's a little bit too much. But during this process, I was thinking about how to, well, different strategies of loading data. So one approach would be to have an AJAX request, and basically what you do, your data is loaded, and once it's in memory, you can do something with it. But if you have millions of data points, well, even with an AJAX request, you can do something else, and at the same time, rendering so many frames, my computer was still suffering quite a bit. So I was thinking about different strategies, and another strategy to load large data sets is to open a stream. And when you open a stream, basically what you're doing is kind of you open a gate and the data comes flowing in. And once a new data point is flowing in, you just write it or you draw it on a canvas and forget about it. So this, for your computer, this is not really heavy at all. It just takes some time. And what you're seeing right now is that the image actually slowly emerges. And once all the data has been loaded, you can save the frame and use it for an animation or something like that. So with that, I would like to conclude my talk. I hope that there were some tips and strategies I used were useful for you. So thank you very much.